we are going to take a look how the Spring, right? Look at this interview scheduling, like architecture candidate speaks. Okay. So, sure, let me walk you through the how a Spring Boot application is structured, how the build process works, how we package the artifacts, and finally how we deploy into an AWS S3, AWS ECS or the Fargate. So, to begin with, right, in a typical enterprise Spring Boot project, the structure follows a very predictable layout. At the top level, we have the root folder containing the Maven or Gradle build descriptors, for example, the palm.xml, or the build.gradle in case if we are using the Gradle. We also have the SRC main Java folder that contains our application code, the SRC main Java main resources folder that contains configuration files, templates, static assets, and so on. And then we have the SRC test Java folder for automated test. Now inside the Java source folder, we usually follow a layered or the hexagonal architecture. In a layered approach, you would typically see the packages like controller, service, repository, domain, common, and so on. In hexagonal or clean architecture, you would instead of find the ports, adapters, and then core, and then enterprises are increasingly using the clean architecture to support the modular deployments and easier for testing. The main class with the Spring Boot application annotation sits at the root package that allow the Spring to scan the sub packages for the beans. From there, the Bootstrap process starts. Spring loads the context, sets up the auto configuration, initialize the bean factory, and then transaction managers, data sources, and then finally it exposes the embedded web container component. So that brings me in the second part, which is how do we build this application in a traditional Jakarta enterprise edition world. We would build the war files and deploy an application server like Apache Tomcat or JBoss or the WebSphere or WebLogic. But in the Spring Boot changes that model. Instead of relying on external containers, Spring Boot embedded into the server, typically Tomcat, Jetty, or Netty inside the artifacts. That means that we can build the project. We are not producing a war file, but usually a fat jar. People sometimes call it as unburned jar that contain the application code plus all the runtime dependencies plus the embedded servlet container. So we run the Spring Boot jar. You are efficiently running your own self-contained application server with an external container dependency. You just do a Java jar app.jar, and then the system comes up with the HTTP port open, reading its config from the application.yaml file or the externalized configuration sources. From the build tooling perspective, we commonly use the Maven or the Gradle to orchestrate the dependency management, code compilation, unit test execution, and then packaging and plugin executions. Then the CI/CD will run the lints, salt, SAST, and unit testing, integration testing, image scanning, artifacts promotion. Tools like Jenkins or the GitHub Action, GitLab CLI, and then TeamCity or AWS Coldbed, can fit into these pipelines. So now the third part is packaging. Spring Boot gives us multiple choices. If someone still wants WAR file, maybe because they are migrating the legacy system, Spring Boot does support the producing the WAR artifacts. In that case, we exclude the embedded server, create a war, and deploy it into the external Tomcat or the JBoss. But in the modern cloud native architectures, especially when deploying to the Kubernetes or the AWS ECS, we actually prefer the executable jar format because it reduces the operational complexity. so that the output of the build pipeline is usually jar files plus the Docker image build from that. So the Docker part is, where it becomes a more cloud native. Typically, the Docker file will be, do something like, pull a base images such as Amazon Corretto, Alphen JDK or OpenJDK, copy the build compiled jar into app/app.jar, exposes the correct container port, maybe, port number is 8080, defining the entry point as a Java jar, app.jar, provide runtime environment variables for configuration instead of backing them into the code. This follow the 12-factor patterns for cloud deployments, especially externalized configuration, stateless runtime, and then disposability. Once we produce the image, we push into the container registry. In AWS, we typically use the ECR Elastic container registry because it integrates with the IAM and then ECS task pools. At this stage, we have our immutable artifacts, the versioned tagged container image stored in a registry. The common then comes the deployment. When we deploy onto the AWS ECS with the forget, we define a task definition. The task definition describes the container image to run, the CPU, and then memory requirements, and then environment variables, and then secrets manager or the SSM parameters or the parameter stores, logging configuration is the firelines or the CloudWatch logs, health check, endpoints, networking modes such as AWS VPC mode. Fargate in particular, right, abstracts all away the underlying EC2 models nodes, so we don't have to manage the cluster nodes, auto scaling groups, patching, IAM roles for machines, or OS security. Instead, task becomes the unit of compute. They scale out using the service auto scaling policy that monitor the CPU, memory, even custom cloud metrics. So on top of that, deployment, we almost always put an application load balancer in front of the ECS service. The ALB handles the traffic routing and then SSL terminations and then sticky sessions if needed. So integrates with the ECS for deregistration during the rolling updates. ECS supports the rolling, but blue green and the canary deployment strategies. Blue green, especially when using the code deploy, the balancer checks the actuator health endpoint if a Spring Boot actuates is enabled, and only routes traffic once the task is healthy. From a configuration standpoint, the runtime configuration is externalized. We don't store the secrets inside the container. We read them, AWS Secret Manager or the SSM parameter store. This allows us to change the configuration without rebuilding the artifacts and is aligned with the immutable infrastructure principle. Once deployed, this task are stateless. Anything stateful goes to the managed services layer, so relational data might go to the RDS or Aurora, caching to Elastic Redis, messaging to SKS, SNS, synchronous orchestration via the event bridge or the step functions, and object storage in S3. The Spring Boot app communicates securely using the VPC networking and then IAM roles and then service mesh or the VPC endpoints depending on the design. So, and finally on the observability side, we plug in distributed tracing and then metrics. Spring Boot integrates with open telemetry and then micrometer and then CloudWatch, Prometheus, and then Datadog to provide the metrics, tracing, logs, health, and then alerts. This is essential for the root cause analysis in the centralized or containerized microservices environment. So to summarize that story, Spring Boot provides the deployment model with the embedded server and layered architecture. Maven or Gradle compile and packaging into the jar. Docker converts into the immutable runtime image. ECR stores the artifacts, ECS, and then Fargate orchestration in it in the production with the load balancing, auto scaling, and then the service discovery, and then an IAM based identity secrets and then monitoring. The whole chain forms a consistent DevSecOps pipeline from the commit to deploy. And that is how we take a Spring Boot workload all the way from project structure on a developer laptop to finally fully managed deployment on AWS Fargate in a modern cloud native setup. Perfect. I'll deliver 40 minutes spoken story. Okay. A 40-minute story. First is Spring Boot project structure plus runtime model. Okay, so at the code level, Spring Boot follows a convention over configuration model. A standard Maven based project has pom.xml file for dependency and then plugin management. SRC mains Java for the server side code, and the SRC main resources for config, and then the SRC test for Java automated test. Within the source tree, we typically impose a layered architecture, controller, service, repository, domain, config, etc. that enforces the separation of concerns. In more modern design, we are shifting toward hexagonal or plain architecture where the code is divided into core domain, ports interface, and then adapters like DB, REST, message broker. This makes refactoring and then testing easier because infrastructure is decoupled from business logic. At the startup, Spring Boot does a few key things: class path scanning, auto configuration, and then bean lifecycle initialization, and then embedded servlet container startup, and then actuator exposure. If we enable actuator, we get actuator health and then actuator metrics, actuator Prometheus, etc. These endpoints become a useful, when later for the container health checks and then observability. And then package model jar or the war file. So traditionally, the Java apps were the war files deployed into external app server like Tomcat, JBoss, WebSphere. Spring Boot inverts that. Instead of war plus container, we embedded the container into the application and then produce a self-contained executable jar with the Tomcat or the Jetty inside it. This is extremely important for the cloud deployments because the immutable self-contained artifacts are easier to containerize. We remove the ops dependency on the external app server and their patching, clustering, and then TLS configuration, etc. Spring Boot can still produce the WAR for legacy migration scenarios. For example, when we are gradually decomposing the monolithic Java EEE applications, but for the cloud native workloads, the jar format is the natural building block. And the third one is build pipeline, Maven Gradle plus plugin. So during the build, we compile, run static checks, unit test, integration test, code coverage, vulnerability scanning, and then artifacts packaging. Maven plugin like the Spring Boot Maven plugin, Maven Surefire plugin, Jacoco Maven plugin, Maven dependency plugin integrate nicely into CI/CD. If we need reproducibility, we pin the versions using the Maven enforcers and BOM provided by the Spring Cloud. External configurations, there are no 12 factors compliance. Cloud native deployments requires the externalized configuration. We avoid the hard coding credentials or the environment specific configuration in application.properties. Instead, we use the bootstrap.yaml or the configuration properties wired to environment variables, config files passed at the deployment, and then AWS SSM parameter store, and then AWS secret parameters. This aligns with 12-factor methodology, specifically config in the environment, statelessness, disposable process, build, release, and then run separation. This makes a container portable across the dev, QA, staging, production, and so on. So containerization Docker. After packaging, we containerize it. The Docker file typically follows a multi-stage build pattern. For example, stage one it's the build through the Maven plus JDK. Second stage runtime JRE, Corretto or distroless. And then the multi-stage reduces the image size, attack surface, and then cloud start latency. For example, instead of 700 MB images, we can get down into 100 MB images or less by using Amazon Corretto base images, Alpine based minimal images, distroless for stricter execution. The container exposes the port number 8080, but doesn't bind it. Container runtimes maps it to host networking. The entry point becomes entry Java access use container support jar. We enable the container memory awareness to avoid the OOM kills in the forget by using the use container support and then tuning heap ratios. Image repository, like the ECR plus lifecycle pipe policies. Once built, we push the images to the ECR electronic container, elastic container registry, and then ECR integrates with the IAM for auth, ECS for task pulse, and then lifecycle policies for pruning untagged images, vulnerability scanning via the inspector, and then immutability, and then tagging strategies matters here. A common convention is semantic version 1.24, git sh 1.2.4 environment alias, like prod qa. We never redeploy the mutable tags like latest in the production, because that breaks the repeatability and then debugging. ECS task model forget the runtime. Basically, now once the images exist, we define an ECS task definition. The task definition is essentially the blueprint for containers. It specifies the container image references like ECR URI, CPU memory reservation limits, and then environment variables plus secrets, logging drivers like typically Firelens and then CloudWatch S3 and so on, port mapping, and then health check, IAM task execution role, and then task role for application IAM access, empirical storage. The separation between the task execution role and the task role is crucial. Execution role allows ECS to pull the images and then push the lags. Task roles role allows the app to call AWS services securely without embedding the AWS key. So then networking mode, like AWS VPC plus VPC design. Basically, when running an forget, we use the AWS VPC networking mode, which gives each task its own ENI, Elastic Network Interface in the subnet. This is extremely powerful for fine-grained security, and then service level isolation, and then compliance, and then VPC endpoints integration, and then auditability. For example, instead of all the tasks sharing a host IP, each task gets own IP and its own security group rules. And then load balancing and then service mesh consideration. We almost always put an application in a load balancer in front of ECS service ALB that performs the L7 routing, path-based dispatches, and then SSL terminations, and then sticky sessions if needed, and then ECS targeted deregistration during the rolling deploys. If the organization operates microservices, we sometimes layer in app mesh, ISO Kubernetes, and then Envoy sidecar, and then MTLS enforcement. Mesh can handle traffic shaping, retries, circuit breaking, and then observability, but not all the environments need the complexity. Deployment strategies critical for interviewers, like rolling default, like replace task progressively, blue green via the code deploy, canary, and then linear, and then shadow trafficking for non-disruptive testing. For highly regulated workloads like payments, healthcare, Blue Green provides the traceability, audit readiness, and then rollback speed. Scaling and then resilience. Scaling on ECS Forget is flexible. We use target tracking, like 60% of CPU, step scaling, and then scheduling the scaling, and then custom scaling via the CloudWatch metrics. Spring Boot plays nice with stateless patterns. For stateless workloads, we extremely state to RDS Aurora for relational data, DynamoDB for key value, S3 for the binary, storage, and then Elastic Cache for caching, and then Kafka MSK SKS for messaging. This eliminates the sticky session dependencies and allow the horizontal scaling, observability, tracing plus metrics plus logs. This is where many interviewers separate junior versus the architect candidates. A complete cloud native workload includes distributed tracing, open telemetry, metrics like micrometer plus Prometheus, Prometheus CloudWatch, Micrometer plus Prometheus or CloudWatch, logs, Firelens, and then CloudWatch or S3, health check, actuator endpoint, SLO dashboard plus alert, typical gold signal like latency, throughput, saturations, error rate. We also enable the structured logs and the correction IDs to trace user flows across the microservices. So, security standpoint, IAM plus secret plus container scanning. Security is layered. For example, IAM task roles for least privileges, SSM and then secret manager for secret injection, inspection for image scanning, WAF for L7 filtering, and then ALB TLS termination with the ACM certificates. Private subnets for the task, VPC endpoints to avoid the public internet routes, and then KMS for encryption at the rest, TLS in transit, and then CloudTrail for audit. We also enable the runtime constraints like read only root file system, no privilege escalation, seccomp profiles like if needed, boundary memory to avoid the noisy neighbor impacts, and so on. And then infrastructure as a code for production environments, right? We don't manually provision. We use IAC stacks such as Terraform, CloudFormation, CDK. IaaS defines ECS cluster, task definition, services, ALV, IAM roles, VPC networking, endpoints, auto scaling policies, and so on. Cost optimization for Fargate workloads, major cost lever include right sizing CPU memory, using Spot Fargate for non-critical workloads, shutting down ideal environment automatically, offloading the static content to CloudFront plus S3, using async queues to smooth the peak loads, reducing the container image size to reduce the cold start, database ideal scaling, Aurora serverless and then data API, compliance and then auditability, like highly regulated workloads like finance, insurance, healthcare requires traceability of deploys and then immutable artifacts, audit log of IAM calls, encryption enforcement, separation of duties, network boundaries control. Using the easiest with private subnets plus VPC endpoints, IAM roles is a strong compliance posture compared to old host level architectures. End-to-end summary, so overall, the life cycle looks like developer writes the Spring Boot code, build via the Maven, package executable jar, container using the Docker multi-stage builds, and then scan plus test plus sign the artifact, and then push to easiest task definition references the images, targets run the task in the VPC, ALB routes the traffic, auto scaling manages load, and then observability handles the runtime, IAC provisions the platform, cost security compliance layered around it actually. Um, yeah, if it is no more like ECS and EC2 and Fargate, we'll think about that. So for both ECS, EC2, and then Fargate, the upstream development workflow is identical. Developers commit the Spring Boot code we build using the Maven or the Gradle, run, test, then package executable jar, containerize using the Docker, and push the images into the ECR. Nothing at the layer is no different between the two deployment models. First, in both models, right, ECS a task definition describes the image to run, CPU memory reservation ports, environment variables, sidecar, like logging and then meshing, etc. IAM task roles and then logging the drivers, secrets. The definition is universal abstraction. What changes between the EC2 mode and then target mode is everything around scheduling, networking, compute the provisioning, and then the life cycle. Now, divergence, compute provisioning model, like, here I am introducing the key contract, like, ECS on the EC2. You the platform, other DevOps team, provision and then manage the EC2 instances that form the ECS cluster. These EC2 instances run the ECS agent and then Docker runtime and the ECS, scheduled task on these hosts. You are responsible for choosing the instance families like CMR, and then sizing the instance type, and then cluster capability, patching, AMI lifecycle, instance scaling, container density optimization, bin packing, cost efficiency tuning. The benefits: if you have deep control over the resources allocation and cost optimization at the scale. EC is on the Fargate, like, with the Fargate, you no longer provision or the manage the EC2 host. Fargate takes a serverless container runtime model. You only specify that the CPU and the memory at the task level. AWS provision the underlying compute. There is no concept of no cluster capacity, no EC2 AMI, no patching, no scaling group. You pay per CPU section and then GB section. This shift the responsibility from the ops team to AWS, and which is why many organizations transitioning towards to the platform serverless as a service model adopt to Fargate. Networking, AWS VPC simplifies the Fargate EC2 model. With the EC2 model, you can run the containers under bridge networking, host networking, AWS VPC networking. Bridge model is cheapest, but NAT host mode is performed but shares host port space. Uh, Fargate mandates the AWS VPC. Every task gets its own ENI and then private IP. This gives clean L3 isolation and then simpler security group mapping and a better compliance posture. This matters in banking, insurance, and then healthcare because auditors loves workload isolation boundaries at the IP level. And then scaling models like cluster level and then task level, EC2 mode. There are two layers of scaling: scale ECS task, scale EC2 instance underneath. Scaling EC2 is handled via the auto scaling group metrics like CPU or container density and cluster bin packing and then efficiency. Poor bin packing leads to resource fragmentation and unused capacity, which is still cost money. Forget mode scaling is simpler. You can only scale the task. There is no cluster capacity constraint. This eliminates two level of scaling complexities. Cost model, like capacity versus the pay per use. EC2 mode, cost efficiency at the scale. With the EC2, you pay for EC2 instances whether tasks are running or not, but you can optimize heavily using the right size reserved instances, computer saving plan, spot instances, bin packing, family selection. Large enterprises with a steady workload usually get major savings here. Target operational efficiency, but higher unit cost. Fargate is no more expensive on a per CPU second basis. It shines for unpredictable workload, highly elastic microservices, dev test empirical clusters, multi-tenancy workloads with the burst patterns. Fargate Spot exist and reduce the cost, but with the eviction risk similar to the EC2 Spot. So the decision becomes, are we optimizing for cost or operational simplicity? Operational burden, ownership model. This section is key for senior architecture interviews, like EC2 responsibilities. With the EC2 mode, you can AMI patching like kernel plus Docker daemon management, and then ECS agent versioning, instance lifecycle, and then security patches, instance health remediation, scale logic, capacity reservations. This is a lot of operational surface areas like Fargate responsibilities, patching, Docker running, agent lifecycle, host security, host scaling, kernel upgrade. Team focus only on application level concerns. Security and then compliance differences, like EC2 mode, right? Security boundary shared node, container share kernel and then C groups. Kernel CVS requires AMI rollout. Multi-tenancy is harder unless you isolate the cluster. Target mode security boundary task. ENI isolation per task, so no sharing for the compliance boundaries, and then no SSH surface patching handles by the AWS. IAM per the task becomes now cleaner. This is very Fargate. This is why the Fargate is now popular in internal regulated fintech workloads. Resource isolation, like with the EC2 CPU and then memory controls are enforced, but noisy neighbor is possible. With the Fargate, CPU memory are guaranteed and then sized per task. This impacts the latency sensitive workloads like trading, payment, or scoring engines. So observability differences, both supports the CloudWatch, but the EC2 gives more metrics such as the disk pressure, and then host memory, and then container density, and then OS level logs, Docker daemon logs. Fargate gives the task metrics and then container logs, and hides the host layer by design. If SRE team requires host node telemetry, EC2 is better. And deployment strategies on both blue green via the code deploy works on both modes. Rolling updates also works on both, but capacity constraints differ. EC2 rolling requires no spare clusters capacity. Target rolling only requires no money. Always AWS always has a spare capacity. This is why fast scaling SaaS companies turned into prefer the Fargate during the growth phase. Multi-tenancy considerations. If your SaaS platform is multi-tenancy, then EC2 cluster you must decide pooled multi-tenant cluster per tenant clusters, namespace segmentation. Fargate, you get the safer tenant isolation by the assigning SG per tenant and ENI per tenant and then IAM per tenant and then VPC per tenant. This simplifies the compliance for ISO, SOC, HIPAA, PCI audit, and so on. When not to use Fargate, right? Architecture maturity shows when you know what not to choose. Fargate is suboptimal when task requires GPU workloads like EC2 is better. You need host level customization, and then you need daemon sets like logging, mesh, service discovery. Workloads requires the extremely high task density. Predictable batch workloads at a scale. EC2 Sparse 80% cheaper. When not to use the EC2, EC2 mode is suboptimal when team lacks the DevOps maturity, workloads are bursty or unpredictable. Compliance requires isolation per workload. You cannot manage the patch cycle. Environment count explodes. Dev QA performance and staging, prod, DR, is etc. Migration narratives like very useful in interviews, like many companies follows with the path, monolithic VM, ECS, EC2, ECS Fargate, VM Kubernetes when they need mesh, custom runtimes or multi-cloud. End-to-end summary. So to sum up, right, at a high level, ECS EC2 optimizes for cost and then control. Fargate optimizes simplicity, security, and then isolation. Both shares the same high-level container orchestration, abstraction, task model, ALB integration, IAM roles, service discovery, scaling, blue-green deployment, observability, and IAC. So choice is not technical alone; it is organizational maturity plus cost plus compliance workload elasticity decision.